there is the concept of total energy, and that means state variables associated and so on. And there is the concept of internal energy, which is the total energy minus the variation of internal energy is the total energy, that part of the total energy which is not devoted to kinetic energy. Okay? But then these are the postulates. That's not proven. As I told you, postulates are something which is not going to be proven. Now we are going to see theorems. We are going to see derivations of that. Okay? From one side, the total energy is, as we saw here, the sum of that, plus that, plus that. These four terms here, right? And on the other side, the energy is the sum of the kinetic energy plus the internal energy, that. And now let's compare. Look, this is precisely the kinetic energy. So from these and these, we see that what is not the kinetic energy has to be the sum of these. So the variation of the internal energy, which is, by the way, the variation of the integral of rho u, small u being the specific contents, is equal to the stress power plus the external thermal power. So this specifically is postulating that in the same way that I told you that the external mechanical power is not an exact differential, there is no mechanical energy in general that we can talk about. In the same way that the external thermal power is not a different energy, a state variable. So we cannot talk about a thermal energy in general. But we can talk about the total energy as the sum of the mechanical power and stress power per unit of time. Then we can talk about an energy, an exact differential, which is the sum of the thermal power plus only the stress power. So the stress power, if you were able to measure the stress power and the thermal power, okay, and measure it through one point in one state to another state, following different paths, the result would be the same. That is the consequence. That's the consequence. Okay? So this says that the sum of the stress power plus the thermal power is an exact differential in terms of the so-called internal energy or in terms of the specific energy, which can be proven like that. And this is the first, in continuum mechanics, is the internal energy balance. It says that the internal energy, so that part of the total energy which is not kinetic, okay? Everything except in kinetic energy that we introduce into the body is spent into produce stress power and produce heat through sources or conductivity, stress conduction. Okay? That is the balance. There is an equality. On one side, I have variation of the energy, internal energy. On the other side, I have reasons for that. Okay? The reasons for variation of this is or variation of the stress power, or production of the stress power, or production of thermal power. Okay? And this is a balance because I have an equality. That's the balance of energy. Global form. Why global form? Because it's defined in terms of integrals. Okay. So let's now see if I can obtain now a partial differential equation, like we did in previous cases. So let's operate a little bit. Look, here I have at the left-hand side, the differential of the total energy, which can be written in terms of the specific contents, that. By the way, this is a material integral, a material derivative of an integral, and look that here we can apply the Reynolds lemma. Whenever I want to obtain the material derivative of an integral and the kernel, if rho times u, I can just do the integral of rho differential of the other thing. So this is a Reynolds lemma. Okay? And on the other side, I have this. The stress power, the source term, and here, well, the term due to conductivity that we already saw that can be expressed in terms of the divergence. So we have that. And that we postulate that this equation holds not only for the whole continuum medium, for the whole medium, but for every part of it. Every part of it. That's important. And that's why here I have emphasized that this equation is fulfilled for every subset of the volume and for every time. And look, that equation is an equation in which everything are volume integrals. So you can group them in just one integral and take differential of b as the differential of the incremental of b, so this subset, as just one particle, one point, and the associated volume. That's what we call localization, and then by localization we obtain that what happens at the level of integrals happens at the level of kernels for all points of the domain. That's a process that we have already done many times. So finally, after that, and look, because of that, otherwise we couldn't have done, because of that I can say that this equation, that equation that was the global form of the internal energy balance in terms of integrals, can be alternatively expressed in a partial differential equation. Why do I call partial differential equation? Because it depends on time. There are derivatives with respect to time, and there are derivatives with respect to space. It's a partial differential equation, which is fulfilled for every point of the domain and for every time. And that is the local form in contraposition of the global form. That's the local form of the energy balance. Okay, that is called also the energy equation. What is it saying? I mean, the same that it said before, but instead of saying it in terms of the whole domain, now it's saying the same, the equivalent things, the counterpart of it, in terms of points, material points. So, look, what is that? U is the energy, internal energy. We know already what is internal energy, the total energy minus the kinetic energy, okay? The total U is the internal energy per unit of mass, because this is small u, the specific contents, and per unit of t. So it's the variation of the internal energy per unit of time and unit of mass. If I multiply that times rho with this mass per unit of volume, that would be the variation of the internal energy per unit of volume and unit of time. So this left-hand side tells us about the variation of the internal energy in a given point of the space per unit of volume and per unit of time. That's what it says. And on the other hand, I had the counterpart of that, the other part of the balance. So what is this variation produced by? Well, first, because at every point, at this point, there will be some stresses at this time. At this point, there will be some strains which vary at a certain rate, and so there will be some rate of strains. And the product sigma times d is a sort of mechanical work per unit of time at this point, mechanical deformation work. So this said that the first reason or the first investment of this variation of internal energy is just producing deformation work per unit of time. Okay? And what is here? Well, here said that is also producing, or due to, the increase of heat in the sources. So this particle may have some sources, heat sources. R is the amount of heat per unit of mass. Rho R then will be the amount of heat per unit of volume and unit of time. So this stands for the one contribution to this internal energy in terms of the amount of heat per unit of volume and unit of time produced by the internal sources. And what is this? Well, this is not so clear because it comes from here through the divergence theorem. But this is the counterpart at particle level, at point level, of the heat conduction, which is lost due to conduction. So finally, if I want to measure what is the repercussion in a given point, in a given particles, of the possible exchange of heat due to conduction transport, not to convective, to just independent of the motion, the repercussion at the level of the particle per unit of volume or unit of time is gradient of Q, where Q is the heat conduction vector. So that is what it says. It's a balance. It's a balance that says that the variation of energy per unit of mass, unit of time, is produced by some mechanical work per unit of volume, per unit of time, the sources, the creation of heat of the sources per unit of mass, unit of time, and the counterpart of the exchange of heat due to conduction. You know? And this is another equation. Look, there is just one equation here. So finally, the first principle of thermodynamics, in our case, translates into one partial differential equation that we have to incorporate to our pocket where we have the equations, and at the end of the day, we'll see how many equations we have and how many unknowns. And we'll try to see if we are able to at least postulate that there is a solution for that via numerical methods or via analytical solutions.